calculator, but we'll see. First, you get a physics problem right. All right, so you have energy in physics. So energy is never created, it's just rearranged. Work is the change in energy on something. So when you change an object's energy, you work on it. So you have an amount of energy beforehand, you have an amount of energy afterwards. That change is the work done. The kind of work we are going to look at is found by doing force times distance. So how hard you push and how long you push for. So when you, well, let's see. What's a good example? Well, when you hit a tennis ball, for example, it applies a certain amount of force, and it makes contact with the ball over a certain distance and changes the energy of the ball. Or when a football player smashes into you, there's a lot of force in the distance that you go. That's the change in energy. A lot of change in energy can be bad for you. So a bullet doesn't go need a very long distance and it's got behind it. That's always a bad thing when it hits you. So I recommend not being hit by anything. Okay, so of course this is calculus class, so you want to know how do I calculate this stuff. So generally, work is F times D. Work is force times distance. However, the problem is the amount of force could change over distance. For example, you have gravitational force. Gravity here isn't the same as gravity high enough. It changes. So the force that gravity exerts on an object changes over a distance. If you look underwater, there's the pressure, the force from the water when you're on the surface, and then there's the force down deeper. So again, that can change. So you can have a variable force, or you can have a constant force. With a constant force, you just do F times D, but if it's variable, then you have to figure out what's going as the force changes at any moment, and that's where the calculus shows up. So work is also, that's a W, you can't tell, force times dx, okay? Where the force is some equation that's always changing. For example, object an object is located x feet from the origin, and the force at that location is F equals x squared plus 4x. Notice the force is different depending on where you are. Okay? At the origin, x is 0, so there's no force. As you move away from the origin, the force gets bigger. Okay? How much work is done in moving the object from x equals 1 to x equals 3? So it is just as simple as integrating that from 1 to 3. It's an easy intro. You should all be able to do that. Let's figure it out. This is x cubed over 3 plus 2x squared from 1 to 3. And you plug in. Okay? Everybody got that? You should be able to get that. Okay. And of course, we have to make this harder. It can't be this easy. So let's do a harder problem. You guys know what springs are. So if you stretch a spring, you have an object that's attached to the spring, you stretch it, it wants to go back, a bungee cord. Or if you push it, it wants to go down. So the spring has a natural resting point, and then you push against it or you pull it, and then it has a restoring force. A force that makes it go back to where it was. And you pull it out, it wants to go in. You push it in, it wants to go out. That's the fun thing about springs. And the springiness of a spring is called the spring constant. It's how hard it is to push it or how hard it is to pull it apart. Okay? And the spring constant, it's really just a measurement of the, like I said, how difficult it is to push or pull a spring. And we call that K. Okay? And the force required to take the spring and either stretch it a distance x or push it a distance x is K times x. Very simple. It's linear. So let's see. A force of 50 newtons is required to stretch a spring from 10 centimeters, x equals 10 centimeters, to x equals 20 centimeters. So far, so good. How much work? Is required to stretch it from x equals 10 to x equals 40 centimeters. Okay. So again, remember we do the integral from a to b of the force times dx. Just to figure out what the force is. And I told you a force of 50 newtons is required to stretch the spring from 10 centimeters to 20 centimeters. So we know F equals kx. So 50 newtons is required to stretch this thing from 10 centimeters to 20 centimeters. So that's a distance of 10 centimeters, which is 0.1 meters. That's why you get stuff wrong in alex, because you don't factor in the units correctly. And then you get another 5 slices of your pie, when you say, but I understood it. And they say, yeah, but you do centimeters. That's happened, I'm sure. So you get K is 500, it doesn't matter what the units are, but they're called Newton meters. That is your spring constant. So now, if I want to stretch it from 10 centimeters to 40 centimeters, I'm going to stretch it from 0.1 to 0.4 of the force, which is kx, right? So that's 500 x dx. Everybody understand that? So you have to do 2 phases in this problem. First, you have to figure out what the spring constant is so you can figure out what the force is. I'll give you this piece of information. 50 newtons is required to stretch it from 10 centimeters to 20 centimeters. Okay? So I use that information here to figure out the spring constant. Right? 50 newtons is the K times 0.1, and I get 500 Newton meters. So now I know what K is, so I know what F is. And the force is Kx, so the force is 500x. And then the work is the integral from 0.1 to 0.4, because it's in meters, 500x dx. So this is 250x squared from 0.1 to 0.4. So that's equal to 40 minus 2.5, which is 37.5. That's correct. I think that's correct. And, if you're wondering what the units is, units are joules. Joules, named after some French guy named Gould. Not Jules as in. So far so good? Can I give you one of these? See if you can do it? Let's give you one of these before we give you a hard one. That's harder. Word problems are fun.
Jackie, you should start saying.
My arm gets hard writing all of this. Okay. The spring has a natural length of 20 centimeters. A 25 Newton force is required to stretch the spring to 30 centimeters. How much work is required to stretch it from 20 to 25 centimeters? Okay? Let's see if you guys can do this. So remember, there's two parts to a spring problem. First, you have to figure out the spring constant, unless we're nice enough to give you the spring constant. Okay? And then you have to figure out how much work it takes to stretch this thing. You could also say compress it. Then you would do the integral from a bigger number to a smaller number. It would go the other way. Alright. So a spring is a natural length of 20 centimeters. It takes 25 newtons to stretch it to 30 centimeters. So the force is going to equal kx. So 25 newtons is required to stretch this thing 10 centimeters, or 0.1 meters, a tenth of a meter. So you solve this, and you get the spring constant is 250 Newton meters. Okay. Now we want to do how much work is required. Yes? Because it's 10 centimeters. 10 centimeters is 0.1 meters. Okay? Alright. The units we want to use are in meters. So when we have stuff in centimeters, we have to convert. Okay? When you do physics or chemistry, you always have to make sure your units are consistent. So when our spring constant uses newtons, then you have to have meters. You can't have centimeters. Okay, because newtons is, yes. It has a natural length of 20, and it stretches from 20 to 30. So it stretches a distance of 10 centimeters, right? It starts off at 20 centimeters, and then you stretch it 30 centimeters, so you stretched it 10 centimeters. Okay? That's your spring. Pull it out. And then you let it go. Point. Alright. So that's tells you your spring constant is 250. Now you want to find the work that's involved. So the work is the force dx. So the work will be the integral from 20 centimeters to 25 centimeters of the force. So remember, F equals kx. So F equals 250 x. So that's 250x. What is that? 250x dx. Okay? Oh, 0.2, sorry. Thank you. Good thing I brought some of you. Actually, you get that. Good. So now we get to do the math. So, let's see. The integral of 250x, 125x squared, from 0.2 to 0.25. So let's see. So that's 125 over 16 minus 125 over 25. So far, so good? That's hard to do, so I'm just going to do it like that. I can do it, I guess. I keep getting a negative number, so I'm doing something wrong. That's alright. It's hard to do in my head. Probably wrong. 15 16ths? I don't know. It's probably wrong. You can check in the calculator. Could be right. Okay, get it? You don't know? Gosh. Who are you people? We break out the TI-84. We do the integral function on the calculator. 45 16ths. That was close. Well, you know, sometimes you win, sometimes you lose. Math 9, integral from 0.2 to 0.25 of 250x dx. Math, enter. 45 16ths. Close enough. You erase this part, and people later will discover this and say, wow, is he good? Okay? That's the trick. It's all done with mirrors. Alright. Were you able to do this problem? Some of you. Now you'd say, what if we give you really obnoxious numbers in the test? Well, we won't. Or we may not ask you this problem. We might ask you something harder. Okay. Now we're going to do the work required to lift a cable or a chain. So, imagine you have a rope, a cable. Well, imagine a rope. So you throw a rope off the side of the cliff, and you're pulling up the rope. Okay? It's easier at the end. It's very hard at the beginning. Why? There's a lot of rope. And the rope has a lot of weight. Every centimeter of that rope has a certain amount of weight to it. So as you pull the rope up, okay, there's less and less hanging over the top. If you've ever pulled a person up, Andy, have you ever pulled a person up? And they weigh a lot less when they get to the top. So doing the rappel thing, right? Okay. So good. You can demonstrate it for us if you want. Okay. So anyway, when they're hanging off, and you're pulling them up, they weigh a lot when they're down there. Sorry? That works. So, anyway, so the rope itself has weight due to its length. Okay? You could just imagine it's coiled up. When you lift a coil of rope, it weighs a lot. If you lift a little piece of it, it doesn't weigh much of anything. So all that rope weighs a lot. So when it's hanging off of something, rope, cable, chain, whatever it is, it's got a lot of weight to it. And as you lift it up, there's less and less involved. So the force is variable, which means you need calculus. Okay? So we'll do the problem that they have in the book first. Time to do some erasing. And I know you're saying if I wanted to take physics, I would have signed up for that class, not this class. Maybe this will help you when physics rolls around. I was lucky I had help at the kitchen table. A 200-pound cable, so we're doing pounds, is 100 feet long and hangs from the top of the wall. Basically, you have a wall, and the cable is hanging down the wall. Okay? And it's going to hang 100 feet. So that's the cable. Okay? There's nobody at the end of the cable because that makes it a more difficult problem. Okay? How much work is required to lift the cable to the top of the building? So now you have to think very carefully. This is the problem with physics. as you lift the cable, you're lifting every little piece of the cable a certain distance. If you say, let's divide this up into distances, and let's call each of those distances x sub I, okay, where I is some moment, some point on the line when you're lifting the cable up, okay? So I is any moment, so, x of 10, x of 11, x of 12, whatever. When you do the numerical calculus, that x of I is going to go away, okay? And then and we imagine the cable is cut into little pieces, each of which has width delta x. So how much does one little piece of that weigh? Well, this is a 200-pound cable. It is interesting that pounds is abbreviated LB rather than something like PD, but that's a French thing. Okay? And it's 100 feet long. So therefore it weighs 2 pounds per foot. That should make sense. You just divide it. It's 200 pounds worth of cable, and it's 100 feet long. So every foot of it weighs 200 pounds. It weighs 2 pounds. So every delta x, the weight of the cable, is 2 delta x. Now weight is a physics term. It has to do with the force. So you would require a force of 2 pounds to lift this cable. And the distance that you lift the cable, that you lift that 2 delta x, just depends on where it's located. So it's located at location x sub I. And then you're going to integrate it from 0 to 100. Because you have to do all 100 feet of it. Okay? So the weight, the force, times the distance, that's the force, that's the distance. Okay? It's actually really the other way around. It's actually 2 delta x, 2 dx times xi. It doesn't really matter. Okay? So again, where do we come up with that? We say, well, any little piece has to be lifted up. Right? If you have some little slice here, it has to be lifted. And some slice here, and then the slice way down there. So all of those have to be lifted. And each one weighs 2x. And each one has to be lifted a distance of x. But the x's vary, so that's why we're integrating from 0 to 100. Okay? No? Do it again? So imagine you're lifting the cable. Okay? The cable is divided into infinitesimally small pieces. You have to lift each piece up. So if the pieces hanging all the way down have to be lifted the full 100 feet. The pieces at the top only get lifted a little bit. So the width of each piece is delta x. Okay? And the weight of each piece is 2 times delta x. It's 2 pounds per foot. And the distance, the width of each piece is delta x feet. We're going to use calculus to do the delta x part. Okay, and then we lift them each some amount of x. So we let delta x get infinitesimally small in terms of the dx. Okay, and we're lifting pieces ranging from a height of 0 to a height of 100 feet. So the very bottom pieces have to be lifted to full 100 feet. The very top pieces only have to get lifted a very small number of feet. And you add them all up. Okay, remember calculus, the integral adds everything up. So this is just x squared from 0 to 100. So that's equal to 10,000, I don't know what the units are, foot-pounds, I guess. In the old pre-metric days, foot-pounds was a useful unit of energy. You'll see it still when you look at like engine specifications for a car. Yes? You have to plug x where? Yes, well, okay, so what happens is the work, the force, did I write that correctly? I'm sorry, I said work, I should have said force. The force is 2 delta x. The distance is x sub I. Okay? So when you do work as force times distance, it's 2 delta x xi. So this is the 2, this is the delta x, and that's the xi. Okay? So again, when you have to lift a rope, chain, anything, actually if you lift a person, okay, when the feet you have their entire body weight at their feet, right? It's easier to lift this part of them than the whole thing. It can be very hard to pick somebody up from their ankles and lift them straight up. Ask anybody who does gymnastics, cheers. Okay? That's why they tend to jump. Or ballet, right? You have to lift them up. They jump, otherwise you can never just bend down, pick them up. Well, maybe Chris could, but most of us do. Okay, or OD. Alright? Got it? So have you tried one? Well, have you tried one? It's important. Before we do the really hard problems. These are the easy problems. This is why, anybody here planning to major in physics?
No.
No? You got one? Oh, we got one! Good for you. Here you go. Engineering is easier. Let's see. A very similar problem. Okay. Are we able to do this one? So this you probably just sort of memorized. It's just like the last one, but with different numbers. Well, that's kind of true. That's not the key to doing well in physics, however. Okay? But again, so the fact that the building was 120 feet high isn't really important. What's important is that the rope hangs completely off the building. What would make it entertaining would be to lift it from some spot way down the building with, say, a very thin string holding the end of the rope to a different spot on the building. But what's going to happen is the weight of that rope at any moment is 0.5 times delta x. So the force is 0.5 delta x, and the distance that we have to lift it is xi. So just like the last problem, we have to lift this thing. So it's a 50-foot rope, so we have to lift it 50 feet. And this is going to be 0.5x dx. So 0.5 is also known as a half, sorry. So the integral of that is x squared over 4 from 0 to 50. So that's 50 squared over 4 minus 0, which is 625. Right? Okay. So you guys ready? Now for the fun one. Okay. We're going to pump water out of a tank. This is fun. Brace yourself. Okay, so you got a tank, and it's shaped like a cone, sure, and it's filled with water, not all the way up. So this is a 10-meter high tank, and it's filled 8 meters up with water, which, by the way, means this is 2 meters. Okay? This radius of the cone is 4 meters. We already know the height. And how much work is required to empty all the water out of the tank? And by the way, the density of water, anybody know the density of water? 1 what? No, 1 unit. What units? But grams per, or cubic centimeter, right. So, since we're in a meter world, it's 1,000. It's 1,000 kilograms per cubic meter, or 1 gram per cubic centimeter, 1 gram per milliliter. Good, it's good enough. Do you know why it's 1? Do you know why it's got a different number? Why is it 1? Because we use everything else based on water. So we call water 1, and then the density of everything else is how dense it is compared to water. Okay. So, this is going to get a little messy, but you guys can do this. So you imagine that you have some spot of water right here, which is located at some depth x sub I. And this is a very thin disk of water. How thin? Delta x thin. Okay, and the radius of this is r. Okay, so let me do some erasing for a second. So to blow that up, as they say, this disk here, this is delta x width, and this is a radius of r. Okay? And that's the water at any spot. So it's just like a chain, except now it's a disk of water rather than just a thin little strip. Okay? So first, let's figure out what r is. We can find r by similar triangles. So if you imagine the spot right here, then we know that r, and how high is this? Well, we're at some spot, delta xi, right? So I'm drawing it correctly. I hope you notice. So the radius is to 10 minus x as 4 is to 10. Okay? Because if this distance is x, this distance is 10 minus x. That's messy, so let's do that again. Okay? This distance is x, so this distance is x. So this distance is 10 minus x. So you have a triangle right here. R is to 10 minus x, 4 is to 10. Okay? Did you see the similar triangles? You have the cone. This is 4. This is 10. This is x. So this is 10 minus x right here. So r to 10 minus x is 4 to 10. Okay? Similar triangles. So to solve for r, so call that 2/5, by the way. And r is 2/5 times 10 minus x. Okay, so volume will be pi r squared delta x. So it'll be pi times 2/5 of 10 minus x squared delta x. I'm going to erase this big cone here because we'll keep this. Okay, so that is 4/25 pi 10 minus x squared delta x. So far, so good? Okay, you guys remember the formula? What's the relationship between mass and volume and density? Sorry. So density is mass over volume, so rho times volume equals mass. So rho, the density, is 1,000. So the mass is going to equal the rho times the volume, which is 1,000 times 4/25 pi 10 minus x squared delta x. Which is 160 pi 10 minus x squared delta x. Okay? Yes? We're getting there. Okay. You're one step ahead. So again, first we just say, look, I have to lift this thing. Okay, so what is this thing? It's a thin disk of water. The water is delta x thin. It's got pi r squared in area. So the volume is pi r squared delta x. I find r from similar triangles, and I plug it in. Now to lift it, the force is mass times gravity, because that's, as you all love physics, how much it takes to lift something, mg. Okay? So we find m by multiplying the density times the volume. And now to get the force, it's mg, so it's 160 pi times g, which happens to be 9.8, times 10 minus x squared delta x. Oh, wow. So far, so good. So how far are we lifting this? Well, this piece of water gets lifted 2 meters. This piece of water gets lifted 10 meters. So we're going to integrate from 2 to 10. You can integrate from 2 to 10. This, okay, times 1 more x, because it's force times distance. So it's 160 pi times 9.8 times x times 10 minus x squared dx. Go ahead, question. Oh, why is it 2 to 10? Yes. Okay. The top of the water still has to get pumped out of the tank. The top of the water is 2 meters from the top of the tank. Okay? So this water gets pumped 2 meters. The water at the bottom gets pumped 10 meters. Okay? The whole thing has to get lifted. Okay? So if you imagine that you just pump that very, very thin surface, that still gets lifted 2 meters. So everything gets lifted 2 meters all the way up to 10 meters to the very bottom of the water. Okay? And then it's force times distance. So the force is 160 pi times 9.8 times 10 minus x squared. The distance is x, dx. And then when you work that out, you get about 3.4 times 10 to the 6 joules. Or 3.4 megajoules. Okay? I think these problems are very hard. You're not imagining if you think they're hard. They're hard to set up. They're not hard to integrate. Okay? It's just very hard to figure out what to do because you have to have a lot of physics knowledge. Imagine that you're lifting this thin bit. Okay? And then the integral part, the calculus part, is that since there's an infinite number of these very thin bits, that's why you have an integral rather than just multiplying x times x. Okay? Because the force is different. The force of the water here has the weight of all the water on top of it. The force of the water here has much less water on top of it. Okay? So at any moment there's a different weight of the water depending on where you are. That's why it's the variable force and all of that. How do we do on this one? And should I go through it again? Go through it one more time. Make sure you guys really get this. Okay. So you have water sitting in a tank. And you imagine you're pumping the water out of the tank. So at any instant, you pump some slice of water. That water has a thinness dx, or delta x. And you have to lift all of those slices out. So imagine that it was just sliced up. Imagine it wasn't water, but it was, pizzas. Sure. There's a big stack of pizzas, all of which are slightly different radii. Okay? So you have a cone of pizza. You have a lot of fun with that. There's a project for Friday night. I recommend doing it with Oreos first. Work your way up. Okay. So each slice of pizza has a width of delta x, has a radius of r. So the volume of the water that you're lifting, okay, is going to be pi r squared times delta x. So what you want to do is you want to figure out the force required to lift it. So to find the force, it's the weight. The weight is mg. Okay, for those of you who haven't taken physics, g is a constant, 9.8 about. Okay, and it has to do with the acceleration of gravity at the surface of the Earth. Now, if you were lifting this really high, g would actually start to change as you go high enough, and things would get very entertaining. Okay, so to find the mass, we need to know the volume, and then you take the volume multiplied by 1,000 because that's the density of water. So the volume is pi r squared times the thinness of the disk of water. So to find r, you use similar triangles. And you say that the radius to this length, which is 10 minus x, and this is x feet, x meters from the top, and it's 10 in total, then it's 10 minus x to wherever you lift it. So you do a little similar triangle, so you get the radius at any moment will be 2/5 times 10 minus x. So the volume is pi times r squared times delta x, which simplifies to this. And the mass is you just multiply by 1,000 because the density of water is 1,000 kilograms per cubic meter. And then you multiply it by 9.8 because that turns it into force, because you take the mass times gravity. Then the work, the energy, is that times 1 more s. Yes? Well, you get to take me the card. Right? So I don't need to give you formulas. You get to fill both sides of the card. I don't know if we're going to have anything like this on the exam. Okay? Personally, I think this particular problem is too hard. I would test you with something like a spring. Okay? But it's not completely up to me. Alright, so now to do this integration, the x times 10 minus x squared is not that hard. You just multiply it out as a polynomial. But the numbers are annoying. Okay, so I might just ask you to set it up. Yes? Okay, so remember, the work is the force times x. Okay? So the force with everything other than the x, then you have to multiply by x. We haven't even done the next one, which is even harder. Okay, which is Wednesday. Alright? I don't have the energy to do another one. So on that note, we'll see you on Wednesday.